Welcome to Supermicro's booth at Supercomputing 21. Welcome to the audience live, and welcome to the viewers on our live stream that is currently live from Supercomputing here in St. Louis, Missouri. Today, I will talk about our supercomputing case study that we've done, and we have now actually delivered and installed with San Diego Supercomputing Center. So let me get into some of the details here. All right, today I want to talk about the Supermicro Habana Gaudi AI training solution. I want to talk about a deep dive or the details of the Gaudi system, and then the San Diego Supercomputer Center Voyager system. So what is a solution in our case? What are we talking about when we say a Habana Gaudi AI training solution? What we have is purpose-built AI training chip from Habana Gaudi. Habana is an Intel company. We have their Synapse AI suite, and we have the Supermicro X12 system and our SuperCloud Composer. So together, this builds an AI training system purpose-built for certain AI workloads. I will get into the details of some of these components, and I will show you what the end result is with the case study for San Diego Supercomputing Center. So the X12 Gaudi AI training system, what is that? As I said, it is a 4U box, and by the way, the box is standing right here behind me, so details can be had. You can meet people and get some very in-depth details about it. But basically, it's a 4U server with 8 of these purpose-built Habana Gaudi AI training processors. It is built around these systems, or these Gaudi processors has a built-in networking. So it's built around the Rocky Ethernet standard. We have a very high performance networking, up to 24 by 100 for scale out. So I will show you some of the interconnect and how this Ethernet is cabled up and how it works. But basically, it's a very strong system, has the latest generation of the Intel CPUs, the Xeons, and memory and lots of in-outs, and let me show some more details about it. So basically, a very powerful system. So the system itself has redundant power supplies, has a bunch of fans, and inside it, as I said, these 8 Gaudi processors. Some of the highlights here is that we can do scale out to other systems. So if you see those little ports we have up here, number 6, these are 6 400 gig ports, Ethernet ports for scale out. So in a total of 2.4 terabit can be used for scale out to other systems. So when we say that the Gaudi training solution is scalable, this is what we mean. We have a very high bandwidth that we can use to scale out to other Gaudi systems. So one of the systems that we're going to show you later scales this out to more than 42 units of these. And this is important for scaling an AI training solution. The ability to scale without any limitations in bandwidth is very important, because that guarantees you a high consistent performance when building very large training systems. Some more details on this. As I said, it's a 4U chassis. It has these slide outs, so you can get to the system to maintain them and update them and so what. And as I said, it's available live so you guys can see it today. So one of the important points of the Gaudi solution, as I said, is the networking. See, most competing solutions require you to use networking cards or additional cards. That means you have to go through systems, and you have to go through PCIe buses, you have to go through network cards to actually do any scale out. What Gaudi has built in is very, very strong networking. So each Gaudi chip has 10 100 gigabit connections. So a terabit of networking built right in to the chip itself. And what it does is that it actually connects each chip to each other in our system. So each Gaudi processor is connected to each other with what a 100 gigabit connection. So that means in an 8 system, 7 are used to interconnect between the chips from each chip, and 3 are used for external connections. So this is how we get to the 2.4 terabit or the 3 per chip, 300 gig channels per chip. So the scale out is very, very, very strong in this. The 400 gig, as I said, you saw the 6 connections on the server itself. Those are QSFP-DD connections. So the way we interconnect these is that we use a 400 gig switch. There's several on the market that are today available, like from Arista and other manufacturers. So using a 400 gig network as a backbone allows you to use this high capacity and use high bandwidth to interconnect the systems. So the important points here, and let me re-emphasize this, it's cost efficient. These systems, the Gaudi system itself, has a 40% higher price performance than competing solutions available on the market. It is easy to use existing models that you have, TensorFlow, PyTorch. The Synapse AI software suite really helps you move and migrate models from other systems to the Habana. The hardware and the software has been designed for scalability. Scalability to a level that is unprecedented, I would say. Of competing solutions, they very often taper off at a certain, when you have more and more systems. In a Gaudi Habana solution, you really can scale up as much as you want. You really double the performance every time you double the number of systems. The AI training workloads that the chips has been designed for is mainly the 3 main ones for this. It's computer vision, NLP on natural language processing, and recommendation. So these workloads is what the chips have been designed for. They're not your general purpose GPUs that can be used for anything and everything. They are focused on these type of AI workloads. But because they're purpose built, they are also very, very strong on for these workloads. So when we say this supercomputing case study, what are we talking about? We're talking here about the San Diego Supercomputer's Voyager research program. So what is Voyager? Voyager is a system built around the Habana Gaudi processors, and a whole lot of them. So the whole system, we're not even showing the whole system here. The first part is the racks of Gaudi processors. There are a total of 7 racks with 6 each of the Gaudi X12 systems. So a total of 42 nodes are in this system just for the AI training. But that's not really enough for doing this. You need networking, storage, compute. So on top of this, there are a bunch of compute nodes, storage nodes. There's networking gear, a rack of networking gear to interconnect all these. And by the way, this design, this shows the real strength of a company like Supermicro. We can build and set up systems like this from one system to whole data centers. We can design it and build it in our labs, in our rack team. They can scale these out to very high capacity, and we can test it, verify it, and then deliver it and set it up at a customer site. This demonstrates the knowledge that a company like Supermicro has attained over the last 30 years, or 28 years, I believe it is. So this system was designed in cooperation with San Diego Supercomputer Center and Habana Labs. So together, the 3 groups here, the 3 companies have designed the system and geared it and balanced it toward these workloads that the Supercomputing Center would like to do research on. And I'll get into some of those cases. What are they going to use this for, and why, and how are they going to use it? So let's look in some more detail. So these photos are actually from last Tuesday. So this is the day the system was cabled up and installed and completed. So that concluded the hardware installation done last week. So very fresh photos. And this shows the 10 racks on the picture on the left, on the right, all 10 racks, and then obviously from another angle. But basically, this is what the installation of this AI supercomputer looks like. And this is how it's set up right now at the San Diego Supercomputing Center. So this was delivered, as I said, last week. So right now, they're doing all the system install and testing and software, and they put the software stack on for all the cases that they're going to study. Formal operation, early access, they call early access, is in January. Formal operation in February. And then they're going to use this for 3 years as a focused test bed. And then 2 years for wider access offered through NSF. So the supercomputer was financed through a grant from NSF, from National Science Foundation. And the grant was used to when you get a grant, you get a certain amount of money. And the way they selected and designed the system was to how much can we get for this amount that the Science Foundation has allocated. So this is how the system was scaled out to get the most bang for the buck. And as I said earlier, the Habana Gaudi chip offers a 40% higher price performance than any competing systems. So for San Diego Supercomputing Center, they felt it was important to get as much power as possible for the grant they had received. So these are some of the reasons behind why they chose us. And we actually did a formal webinar with them last week, and that actually might be worth looking at, because one of the deputy directors for San Diego Supercomputer Center actually talks about all this in details on how they selected and how they designed it together with us. So what does it actually contain? As I said, 42 training nodes, each with 8 Habana Gaudi processors, so in total of 336 processors. Each system also has 3rd generation Intel Xeon processors, latest. Each node has 6 terabytes of node local NVMe storage. There are 2 inference nodes, so Habana also does an inference based PCIe card called Goya. So there are 2 nodes with 8 each of these Goya processors, and that's going to be used for live and production testing of inferencing systems. On top of this, there are, for other workloads and other tests and research they're going to do, there's 36 x86 2-socket compute nodes. So a lot of compute power is available in this system as well. The network is built around the 400 gig Arista switch that really binds the whole thing together and ensures that we can run all the Gaudi processors and nodes in full concert. The storage system, about 2 petabytes, and they're going to experiment with a number of different storage systems. Some of them like Ceph, Lustre, and various others that they're going to play around with. Some even, I think I mentioned in this hall somewhere today. So a lot of research will go into this. So the deep learning frameworks, TensorFlow, PyTorch, as you know it from most of the deep learning environments today. And then obviously the Habana Synapse AI development system. By the way, there's a lot more information available online, and there are a couple of links here. And we can also share the links after the show with anybody who's participated. But there's a depth of knowledge, both on the Supermicro and the Habana side, about the solution and about this system in itself. So the Voyager system, the actual rack level design, we have reference designs for that as well. So if anybody's interested in those details, it is available from Supermicro to show how we can scale up to really very powerful and very large systems. There's also a solution brief that you guys can download, and it's on the website live, and we have links to it also here in the booth. So what are they going to use it for? Why are they building this AI supercomputer? And I think this is where it becomes really interesting, because what is the impact for a research organization like San Diego? What's the real value here? So there are a number of areas they're planning to do research in. I will highlight two of them. And these slides, by the way, as you can see, I borrowed them with permission from SDSC. But basically, some of the really interesting stuff is going to happen in astronomy, atmospheric research, biophysics, computer science, pretty much all the areas that they cover. But two of them I'm going to highlight, and one of them is particle physics and the satellite image analysis. And for those specific cases, I will show you some of the details. So, what is it that we're talking about? Why do you use a supercomputer for anything in like high energy particle physics? Well, some of the data coming out of the Large Hadron Collider in CERN in Switzerland, the data that comes out every time you do an experiment is in petabytes, and it's hundreds of terabytes per second, right? So the amount of data coming out is too much for you to analyze it all. So what you do is you do have some high-level triggers. So once you see some event, and these high-level triggers are really based on AI and learning about the data that are coming out, right? So first you do a high-level trigger, and then you go in to do AI on those data sets following that trigger. So the interesting part here is that this will be used to detect future particles like the Higgs boson, which came out of those data sets, right? So the only way you can really analyze data sets this large is today through AI and systems like this. So this is one of the primary tools for the research that they're going to do for the next couple of years at San Diego. So they have a whole team built around it. Javier Duarte is one of the leading researchers there, and he's running that program. So I think as I was told, they're going to use the GNN, the graph neural networking on some of this data to improve the particle identification and event reconstruction. And the Goya inferencing adapters are also being used for software-based triggering. So the whole data processing is going to run through the Goya and the Habana to do this. So this is one example of what they're doing in the high energy physics application. Another interesting example is the analysis of satellite imaging, and specifically when we talk about wildfires, and for people like myself living in California, wildfire has become a new norm. We've gotten used to wildfires. So there's now a lot of research institutions focusing on how can we better prevent wildfire, how can we handle wildfire situations, what can be done from technology's point of view to try to alleviate the situation. AI can't just magically like get wildfires to go away, but we can do a lot in prevention and understanding the topography, the landscape from satellite imaging to figure out how to better manage it, how to better determine regions and move people around for let's say organized refugee camps and things like that. So this is I think an example that I feel is very, very interesting, because this will potentially affect us all down the line when we become better at managing the wildfires that we're now living with. So and what they're doing specifically is they're applying the deep learning to satellite image analysis and disaster management. And the Voyager project is deep learning algorithm to determine the land covers across all the different areas and contents of wildfire management. And there's actually, they have a little website as well that talks in details about it. But basically, goal is to combine all the AI models, from fire science models and fire science expertise. Study and simulate fire behavior under different conditions. So this is one of the key things they're gonna do with that. I think, and I know from talking to San Diego Supercomputer, these are just a couple of examples of all the many things they're going to use these systems for. This is going to be a very powerful tool available to them as a research institute or research center to go in all areas that AI can be of use and be of benefit. So this is the Voyager system that San Diego has put together. But I will say, as part of Supermicro, and for the last couple of months been involved in this, it's a project that we're very proud of, and it's a project that shows the ability of a company like Supermicro, the knowledge we've built over the years, and how we can put very complex systems together, and how we can work with some of the leading developers out there of AI processors, and together create solutions that potentially can make an impact and a change in the environment around us for years to come. So this is, I think I was a little fast, but this is what I had to say about our system today. I'm happy to take any questions you may have. If there are any questions at all, if I can't answer them,